Now we'll talk about the airframe and structure subsystem. We were responsible for the making of tubes, couplers, and the nose cone of the rocket. For the tubes, we used a ABS 3D printed mold that when we added acetone, it would get really smooth, so the outside of the rocket would also get smooth. We used the lamination process for making fiberglass and carbon fiber tubes. The fiberglass tubes were only used in the Avionics subsystem. We used aluminum couplers. These were all designed, drawn, and made by the students here at one of Vita's laboratories. And for the nose cone, we use the old fiberglass nose cone that we have. It was designed by a student about 2 or 3 years ago.
Structure subsystem works together with every other subsystem by analyzing each component of the rocket using computer programs like FEMAT to analyze loads and torques, for example.
With that, we can guarantee the integrity and principally the safety of the rocket structure, during handling and the flight.
As for the propulsion subsystem, here you can see the general scheme of the motor, which is composed of the bulkhead, the case, the propellant, and the nozzle, which is divided in 3 sections: the convergent, the throat, and the divergent. The green propellant has an internal design of a 6-pointed star with both the upper and bottom surfaces coated with liner, in order to obtain an approximately constant thrust throughout the burn, and it is also covered with nitrile rubber for thermal protection of the case. The nozzle is made of aluminum, but the throat specifically is made of graphite, because it has to withstand the maximal thermal stress. It has a conical design to simplify the manufacturing process, and the analysis showed no significant penalty in performance. The simulations were made with a software developed by the Institute of Aeronautics and Space, as well as with the software BurnSim, in an iterative process with the flight mechanics subsystem in order to optimize the motor.
In Flight Mechanics subsystem, in the beginning of the project, we use a team-made simulator which considers only 2 degrees of freedom for the rocket. Further, when the main parameters of the rocket are obtained, we use a team-made 6 degrees of freedom simulator besides OpenRock to simulate the flights. The predicted apogee is 3070 meters, and this year we had worked on an air brake in order to get an apogee closer to the target. The other information were provided by the 6DOF and OpenRock simulators.
In the Aerodynamic subsystem, we divided our project in simulation and experimentation. First, we focus on the predictions with MVO and our CFD software. And in order to improve that, we made a test rocket and took it to a wind tunnel so we could measure the coefficients with and without the air brake activity, for example. By doing that, we can make the final project the most accurate to our needs and goals for the competition.
Avionics are responsible to gather and store accurate flight data such as position, trajectory, and velocity, and to transmit the real-time location to the recovery team on site. The diagram shows what we assembled: an Arduino Duo, a GPS, a accelerometer and gyroscope module, a magnetometer, and a featherweight tracking system.
I'm going to explain in brief about our recovery system. It is composed mainly by the drogue and main parachute and the avionics. Both parachutes, when in their compartments, are accommodated in a flame-proof sack and share space with 2 independent ignition charges plus wiring. The drogue parachute is developed to open near the apogee altitude in order to establish a higher preliminary speed. The main has its opening in a lower altitude than the drogue, so that the rocket can achieve the desired terminal speed. The flight electronics are composed of 2 easy mini altimeters, 2 9V batteries, 2 RBF switches, and lead wires to the ignition chargers in both parachute compartments.